So here we have a rhombus surrounded by two arcs. The fact that they're calling them arcs means that they are part of the circumference of the circle. So we just need to look a bit carefully about which ones. So arc BAD has centre C. So this is arc BAD and with the centre C. And then we're told arc BCD has centre A. So that's that arc with centre A. And I could draw it out separately to have a look at it there. So to find this sector area, we need this angle here, which is going to be the same as this angle up here, angle BAD or angle BCD. So to find this angle, we could be looking at cosine rule. And we would need to find the length BD before we could find that angle there. Not immediately obvious, but look carefully. We need a bit more information, and we find this measurement here, 4 centimetres. So that means that's going to be 2 centimetres and 2 centimetres there. I can therefore use Pythagoras' theorem to find the length of BO. And we find this is 2√3. This other side would also be 2√3. So the whole thing here would be 4√3. Using that, we can then use cosine rule to find angle C. So we get this rearrangement with the values plugged in. Remember, with the cosine rule, this B and C, these are the sides that are either side of my included angle here. So from there we can find C. We find C is 120 degrees. We could work in radians here or degrees, it doesn't matter. When we come on to use our area, we'll just use the appropriate area depending upon whether we're in degrees or radians. So if we use in degrees, we get sector area theta over 360 times pi r squared. It's our fraction of the circle, using 120 degrees, and we get this value for our sector area. Suppose we use the radians formula. This time we use half r squared theta, where theta is given in radians, and you can see if we just plug that in, our radius is 4 theta, 2 pi over 3, we get exactly the same answer. So it doesn't actually matter if we're working in degrees or radians, as long as we're using the correct formula. We would then just look at the area of half of the rhombus and look at it as an area of a triangle. So it's a half times the base times the height. So that gives us 4√3. So if I just look at this shaded section here, just those two parts, so the area of those bits is going to be my sector area, 16 pi over 3, minus the area of that triangle. I say it's going to be minus twice the area of that triangle, isn't it, the rhombus? So rhombus must be 8√3, so minus 8√3. So that's that area there. So my full area of shaded bit is twice that. If I then take this fraction of 1/3 outside my bracket, so factorise that out, 2/3, 16 pi, I'm going to have to multiply this 8 by 3, so minus 24√3. So that when I then multiply it back out, I'll get back to my 8√3, which is what we needed to show.